Next, we have Abhishek Das, who is a PhD student at Georgia Tech. Abhishek led the organization of the Visual Dialog Challenge, and he's going to tell us more about the challenge, announce the winners, and present some analysis of the results. We're looking forward to hearing from you, Abhishek.
Test. Right. Hi, everyone. I'm Abhishek. I'm a PhD student at Georgia Tech. I'm going to be presenting overview, winner announcements, and analysis of results for the Visual Dialog Challenge this year. So let's begin with an overview of the task, dataset, and challenge. So the task in Visual Dialog is to build agents that can see and talk. So here's an example. Given this image, a machine might generate a caption such as a man and a woman are holding umbrellas. A human might ask a follow-up question such as what color is his umbrella? To answer this, the model has to understand which person the word his refers to, focus on the umbrella held by that person, and then respond back in natural language. A human might ask another follow-up question such as what about hers? To answer this, the model has to understand which person is being talked about, the object that was referred to in the previous rounds of dialogue, zone in on the color of that, and then be able to respond to that in natural language, such as hers is multicolored. A human might then ask another question, such as how many other people are in the image? This requires more complicated reasoning. The model has to keep track of how many people have been talked about in the dialogue history so far, reason about occlusions, and then count the remaining people, and then respond back with an answer such as, I think 3, they're occluded, and so on. So why do we care about this task of visual dialogue? So this has wide-ranging applications. So for example, if there's a robot that's in some sort of a hostile environment, natural language is a very intuitive interface to be able to talk to that robot and instruct it to go to a specific room or ask questions about its environment. Visual dialogue is also useful to aid visually impaired users. So for example, here, Peter uploaded a picture from his vacation in Hawaii, and a visually impaired user can ask questions about that image. Great, is he at the beach? And the model responds, no, on a mountain, and so on. There's also a use case for situationally impaired users, where for example, in the case of surveillance, where there's so much visual data that it's infeasible for a human to sieve through all of it manually. And so it makes sense to have some sort of an intelligent agent that can look at the entire corpus and then answer questions in natural language. So concretely, the task of visual dialogue is that given an image, a dialogue history consisting of a sequence of question-answer pairs and a follow-up question, the machine has to predict a free-form natural language answer. We started by collecting a data set for this task by pairing 2 humans on Mechanical Turk. So on the left, there's a questioner who's shown the caption but cannot see the image. And on the right is the answerer, so they can see the image as well as its caption. And the task for the questioner is to ask questions to be able to imagine the scene better. So for example, here the questioner asks, is the man wearing a helmet? The answerer responds, no, he does not have a helmet on. The questioner asks, how old is the man? He looks around 40 years old. What color is his bike? It has black wheels and handlebars, and so on. So version 1.0 of the VisDial dataset contains dialogues on 130,000 images from COCO. We have 1 dialogue per image, and each dialogue has 10 rounds of question-answer pairs for a total of 1.3 million dialogue question answers. And all of this data is publicly available on visualdialog.org. In our CVPR paper a couple of years back, we had proposed an evaluation where models are shown candidate answers consisting of nearest neighbors, popular, and random answers from the data set for each of these questions. So here's what some of those answer options might look like. And the task for the model was to rank the ground truth answer as high as possible. and the model is evaluated on how well it ranks that ground truth answer on retrieval metrics. However, over time, we've noticed that this can often be sort of a noisy evaluation. So here's an example. Here's the caption: the 3 elephants next to one another near a blue body of water. There's a dialogue history, and then there's a follow-up question: are there any people? The ground truth answer from the data set is no, but there can be multiple ways of saying the same thing. So evaluating based on a single ground truth answer can often be problematic. Here's another example. So in this case, the caption is some donuts on a plate with different letters. There's a dialogue history. And the follow-up question is, does this look like a restaurant setting? The ground truth answer is no. But of course, this is an ambiguous setting. And so there are multiple ways of answering this question, such as I cannot tell, that's hard to tell, probably not, and so on. So to address this to some extent, what we did was we collected dense annotations on the test set for evaluation in Visual Dialog. So what we did, so this is, for example, what the mechanical Turk interface looks like. We show humans. Sorry, a lot of this work was led by Ayush, who's a research scholar in our lab at Georgia Tech. So what we do is we show humans a caption, a dialogue history, and a follow-up question, and 100 candidate answer options for that follow-up question. And so these annotators mark each of these 100 answer options as relevant or irrelevant, and we collect 4 annotations for each question in the Visual Dialog test set. And the ground truth relevance for each candidate answer option is given as the number of annotators who marked that answer as relevant divided by 4, which is the total number of annotators that we got these relevancy annotations from. So now for each question in the test set of Visual Dialog, we have 100 candidate answers, and for each candidate answer, we have annotations for how relevant it is for that question. So here are some examples of what these relevance scores look like. So for the question, are there any people? Answers such as no and other ways of saying the same thing have high relevance. Then answers such as no humans, I don't think so, 0 visible, which are slightly different ways of saying, different ways of answering the question, have slightly low relevance, and so on. And here are relevance scores for the second example that I showed earlier. So the ground truth answer that we originally had in the VisDial data set was to the question, does this look like a restaurant setting, was no. But when we collected relevance scores for all the 100 candidate answer options, the options that were highly ranked conveyed a fair amount of uncertainty, such as I cannot tell, that's hard to tell, and so on. And so to evaluate submissions to evaluate predictions using these dense annotations, we use the NDCG metric, which is sort of a common metric from the information retrieval literature for non-binary relevance scores. So here's an example of how that works. So given answer options such as 2, yes, probably, no, yes, it is, for any question, ground truth relevances might look something like this. So the correct answers, or the relevant, the answers with non-zero relevance here are yes, yes, it is, and probably. And so that's what the ideal ranking of answer options might look like. And let's say a submitted ranking looks something like this, where the top 2 answers are the same as the ideal ranking, but the third ranked answer is 2, which has a relevance score of 0. So the way here's, I'm going to walk you through an example of how NDCG is computed. So we first we iterate over all the answers with non-zero relevance scores. So for example, here, K would be 3. K is the number of answers with non-zero relevance scores. I iterates over the rank of the answer. So here, I equals 1 would mean the answer yes. I equals 2 would be the answer yes it is for both of them. And I equals 3 would be the answer probably for the ideal ranking, and 2 for the submitted ranking. And so the ideal DCG for the ideal ranking of these answer options can be computed in this way, where these relevance scores are, the first relevance score is the the first factor here is the relevance score for the answer yes. The second factor is the relevance score for the answer yes it is. And the third factor is the relevance score for the answer probably. And so the ideal DCG is 1.88. Similarly, the DCG of the predictions can be computed. So here the first factor corresponds to the relevance of the answer yes. The second factor corresponds to the relevance of answer yes it is. And the third factor corresponds to the relevance of the answer too. So now that we have the submitted and the ideal DCGs, NDCG is computed by dividing the DCG for the submitted ranking by the DCG for the ideal ranking. And that would be 0.87 in this case. So a few salient points of how this metric works with these dense annotations is that one, the first and key point is that this takes into account multiple ways of answering a question, which is desirable. Next is that swapping options with the same relevance score does not affect the NDCG. And finally, after the first K ranks, shuffling the ranking of options does not make a difference to the NDCG score. So what that means is that we only care about the candidate answers that have non-zero relevance scores in the annotations. And so we believe this is more robust than the earlier metric that we had because this takes into account multiple candidate answers, and this is what we use to pick winners in the challenge. Coming to the challenge itself, it was hosted on Eval AI, just like last year. A lot of that work was led by Rishabh, who's a research scholar in our lab at Georgia Tech. The code for Eval AI is publicly available. It's an open source platform for hosting challenges. This is, for example, what it looks like. And this has sort of become a standard challenge hosting platform, at least in the vision and language community. One thing that I really like about Eval AI is how easy it makes to plug in custom evaluation scripts. So for example, this is a code snippet of how we compute NDCG given a set of annotations and predictions. And we can just plug this in and look at these metrics on the Eval AI leaderboard. Coming to the splits of the data set, the training split has dialogues on 123,000 images from COCO. The validation and test splits have 2,000 and 8,000 images respectively that are not from COCO, and I'll get to that in a bit. The validation split has 10 round dialogues. For the test split, we evaluate on one round for each dialogue instance. And so the reason why we use COCO-like images but not images from COCO test is because the dialogue history in Visual Dialog has the caption, and so releasing captions for the test split will compromise the integrity of the COCO captioning challenge. And for the test set, we have one round evaluation because the dialogue history contains answers to previous rounds in dialogue, and so that makes it infeasible to evaluate those answers. Coming to the challenge phases, we had 3 phases: the val, test standard, and test challenge. The val phase is intended primarily for debugging and testing the evaluation server, so there's no limits on the number of submissions. The test standard phase is meant for reporting numbers in papers and so on. And the test challenge phase is what we used for the Visual Dialog challenge. We've also released starter code in PyTorch, which was primarily effort led by Karan, and we have heard back from a lot of teams that this has been extremely useful for them. There's also a Lua Torch implementation that was initially released as, along with the paper, but it is gradually going out of fashion as people move to PyTorch. So models typically for Visual Dialog are built in an encoder-decoder manner. They have, the reason I wanted to bring this up is because there can be 2 kinds of decoders that you can use for a task like Visual Dialog. The generative decoder does not have access to these candidate answer options during training, and so during training, it's maximizing the likelihood of the ground truth human response. During evaluation, though, we look at what the likelihood scores. We rank options by the likelihood scores assigned by the model to these candidate answers, and evaluate on the retrieval metrics I talked about earlier. The discriminative model has access to these candidate answer options even during training, and so can learn correspondences between which options are more likely and so on. Right, so coming to the challenge stats and winner announcements, this year we had more than 500 submissions across all phases. There were 37 submissions to test challenge from 10 teams spread across 9 countries. The winning team this year is team MReal BDAI with an NDCG score of 74.57. They get $10,000 courtesy $10,000 of GCP credits courtesy Google. And I'd like to invite the team members up here, and we will hand over the prize. Jiaoshen Qi, Yulei Niu, Han Wang Zhang, Jian Qiang Huang, Xian Cheng Hua, and Ji Rong Wen. And they'll, of course, be presenting a talk on their approach right after my talk. So let's look at some brief analysis of results of this year's challenge. So the top 10 teams by NDCG, the first is, of course, MReal BDAI with an NDCG of 74.57. The second team is MSD365 AI with an NDCG of 64.78. So there's a massive gap between the first and second teams. The third team is VICSNU with an NDCG of 62.04. There's a tie for the fourth position between Square and DL61, and so on. So as you can see, there's a massive gap between the first team and the rest. Concretely, the first team got an NDCG score that's 23 points higher than some of our baselines in our initial work. The winners of last year's Visual Dialog challenge had an NDCG score of 57.75. So this is a pretty significant 16.82 improvement on NDCG. It's also, like I had mentioned earlier, NDCG as a metric takes into account these dense annotations where for every question, multiple candidate answers can be relevant. And MRR was our earlier metric that takes into account only a single ground truth answer. And so if we look at how these teams stack up against each other in terms of MRR, the story is a bit different. So for example, here, IDAN SC is the top team according to MRR of 69.6, and MReal BDAI is close to the end there with a score of 53.37. So we wanted to dig deeper into this and try and understand what are the concrete differences in the kinds of predictions between models that are doing well based on NDCG and models that are doing well based on MRR. So we compare MReal BDAI and IDAN SC. Here are the MRR and NDCG scores. So IDAN SC was the best team according to MRR, and MReal BDAI was the best team according to NDCG. So here I'm showing the distribution of answer predictions for these two teams. So as you can clearly see, there is significant difference in what the kind of answers these models predict for the at least in the head of this distribution. So here, for example, the best team according to MRR has a very peaky distribution on answers such as yes and no, and I cannot tell. The best team according to NDCG, for example, has a much more diffuse distribution. And this is, so it sort of learns to place its weight on multiple answers that can mean similar things. So for example, I cannot tell, I can't tell, I think so, not sure, I don't think so, yes it is without the comma, yes, and so on. And I wanted to sort of tie it back to the example I showed earlier. So for example here, for the question, does this look like a restaurant setting? The ground truth answer is no, but of course, that is subjective to quite an extent, and there can be multiple ways of answering that question. And so a model that learns to, because the data set was collected in a way where the person asking questions was not looking at the image, there are a whole bunch of these hard binary questions that can have multiple ways of answering it. And so a model that places its weight, its mass on some answers that convey uncertainty are generally doing a better job. If we break down the performance of these teams by the starting bigrams of the question, you can see that there's a uniform, the best NDCG team does well uniformly across questions. But one thing worth noting is that a large part of the Visual Dialog dataset has these binary questions. So I've underlined all of the starting bigrams that refer to binary questions. And this is where most of the improvement is typically coming from. I also wanted to briefly talk about a way in which NDCG can potentially be, so NDCG is generally a better metric than MRR, but I also wanted to talk about a way in which NDCG can potentially be gamed. So in our internal experiments, we've looked at how discriminative and generative decoders with the same encoder stack up against each other on these metrics. So code for this is available on GitHub. Here is what their MRR and NDCG scores look like. We are specifically interested in the difference in these NDCG scores. So if we look at the predictions versus the answered option length for both of these models, there's a clear skew here. So for a discriminative model, there's the story here is fairly uniform in that it learns to, it doesn't care all that much about the length of the answer. Whereas in the case of generative models, we see that they rank these shorter answer options much higher than longer answer options. So for example, answers of length 1 and 2 are ranked higher on average than discriminative models, and the story flips for longer answers. And if we break down the accuracy between these generative and discriminative models based on binary and non-binary questions, we see that the generative model does significantly better primarily on these binary questions. And these binary questions are the ones that have a lot of yes, no, and related short answers. And so even without looking at the image, for example, these generative models can learn to exploit this and do well on NDCG. So to summarize, the winning team this year had an NDCG score of 74.57. This is a 23% improvement over baselines and a 17% improvement over last year's challenge winner. We see that models doing well on NDCG spread belief over multiple relevant answers, which is great, which is desirable for a task like Visual Dialog. But of course, these dense annotations have many short answers that generative models might learn to superficially exploit. So for example, if we, and since there is value in developing generative models for Visual Dialog, if we are interested in building models that can generate rich, diverse, longer answers, then NDCG might not be the best metric to be looking at. That's it. Thank you. I'll be happy to take questions.